Having defined equivalence classes and partial orders, we next define something called equivalence class. It is defined for an equivalence relation with some underlying set. Consider this set A equals 1, 2, 3 and an equivalence relation R, which is 1, 1, 2, 2, 3, 3, 1, 2 and 2, 1. It is defined for each element in the underlying set, which means I can talk about equivalence class of 1. We use the subscript R to denote the underlying relation. The definition is this: for an element A belongs to A, equivalence class of A is set of X such that X comma A belongs to R. Now let's look at the equivalence class of 1. It is set of X such that X comma A belongs to R. X is 1, 1 comma 1 belongs to R, and X is 2, 2 comma 1 belongs to R. Set of X such that X comma A belongs to R. I am including this because 1 comma 1 is in R. I am including this because 2 comma 1 is in R. So similarly, you can talk about equivalence class of the element 2. You see that 2 is present because 2 comma 2 is in R, and X comma A, which means 1, and Y 1 comma 2 is in R. Now let's look at it as a set, so order doesn't matter. 1 comma 2 and 2 comma 1 are one and the same. Equivalence class of 3, X is just 3, so 3 comma 3 belongs to R. Suppose the equivalence relation is 1, 1, 2, 2, 3, 3. Then we see that equivalence class of 1 with respect to R2 is 1, and 2 is 2, 3 is just 3. X comma A belongs to R, X comma A belongs to R, X is 3 because 3 comma 3 belongs to R. Since in all equivalence relation we find 1, 1, 2, 2, 3, 3, and if you look at equivalence classes, you see that in 1, 1 will be present, in addition to that something else. In 2, 2 will be present, in addition to that something else. It is never the case that equivalence class is an empty set. Okay. Note, since R is an equivalence relation, for all A belonging to this, the set equivalence class is not an empty set. At least A will be present, and A belongs to A, this is 1. For all A belongs to this, A belongs to equivalence class of A. Consider one more. Let's look at R3 to be A cross A itself, which means equivalence class of 1 as 1. All possible pairs are present in A cross A. So I include 2 because 2 comma 1 is in R. I include 3 because 3 comma 1 is in R. Next, let us look at equivalence class of 2. and it has 1 because 1 comma 2 is in R. It has 2, 2 comma 2 is in R, 3, 3 comma 2 is in R. Next, let us look at equivalence class of this. So you see that 1 is present because 1 comma 3 is in R, 2 is present, 2 comma 3 is in R, 3 is present because 3 comma 3 is in R. Now the interesting part over here is the equivalence class of 1 is same as 2 is same as 3. Now if you look at this, these two are same, this one is different. In this all three are different. Look at it this way. You look at any two. If you look at 1 and 2, they are same. Look at 2, 3, they are same. You look at any two, say 1 and 2, they are same. But look at 1 and 3. They are different. Their intersection is empty. That's very important. Their intersection is empty. So if you look at any two equivalence classes, we see that they are identical, same, or this and this, their intersection is empty. That's another property. So for all a comma b belonging to this, if you look at the equivalence class of this and this, so either these two are one and the same, or you see that the equivalence class of this intersection, this one is an empty set. If you look at any two, you see that it is same, or if you look at these two, they are empty. If you look at any two, they are empty. Okay, so there are a couple of interesting other properties as well. If you find, say, 2 in 1, then you find 1 in 2. If you find 3 in 1, you find 1 in 3. Correct? So the fourth one is if B belongs to the equivalence class of A, then A belongs to equivalence class of B. Simple reason, R is an equivalence relation, which means R is symmetric. Now, why B belongs to this? Definition says it is set of X such that X comma A belongs to R, which means B comma A belongs to R, and R is symmetric. Therefore, A comma B belongs to R. If A comma B belongs to R, then we see that A belongs to equivalence class of B. Okay, so there are a couple of other interesting properties that one can observe. Consider this equivalence relation. R is 1, 1, 2, 2, 3, 3, 1, 2, 2, 1, and 1, 3, 3, 1. Now, if you look at this, 3, 1 is present, 1, 2 is present, so I am forced to include 3, 2 because it's an equivalence relation. And similarly, 2, 1 is present, 1, 3 is present, I am forced to include 2, 3. So now this becomes A cross A. Okay. So the point that I am trying to make is 1, 1, 2, 2, 3 3 3 1. So this is perfect. This is an example equivalence relation. But when we try having just 1 2 2 1 1 3 3 1, and that was not satisfying transitive property, so we were forced to include this. Correct? But when we add this, so the idea is this: you have an equivalence class. This was having 1 2. Because of that, this was also having 1 2. And because of 3 3, we were having just 3 here. But if you just focus on this, then the idea is to have an equivalence relation, subsequently equivalence classes, something of this form. So something like 1 3. If you have 1 3, then 3 should also be 1 3. Then 2 will be just 2. When you include 2, that was the point I was trying to make here. When you include 2 here, then this becomes 1 3 2. And one of our properties says if 2 is present in 1, then 1 must be present in 2 as well. Okay, so that will bring 2 1. Now you see that 1 is present in 3 and 3 is present in 1. And the other part is this. So if you bring 2 inside, what happens? 2 is present in this, so therefore you will be forced to include 1 here. Okay, fine. Now you get 1 2, and so I am trying to give you a larger picture. So 1 3, so let me include 2, then look at 2, then let me include 1, then look at 3, this. It's not complete. So the point I am trying to make is on this side you are forced to include these two because of transitivity. Similar thing you can see when you build equivalence classes also. Suppose you start with this, then you try including 2 into this. Suppose it becomes like this, 1 3 2. Now because 2 is present in 1, then you are forced to include 1 in 2. Okay. Now is this satisfying what we want? Okay, let's see. 3 is present in 1, and so 1 is present in 3. Okay. What else? Now look at 2. 2 is present in 1 and 1 is present in 2. Now is this satisfying what we want? Okay. But there is a gap. You see that 3 is missing here, and you see that 2 is missing here. If you look at the underlying relation, we observe that this is not an equivalence relation. Okay, let's look at that. Now from this, you know that 2 1 belongs to R, and from this we know that 1 3 belongs to R. Because R is transitive, it means that 2 3 belongs to R. And we know that R is symmetric Therefore, 3 comma 2 belongs to R. So now 2 3 is present, which means x comma a, we need to include 2 into this. 3 comma 2 x comma a, so we need to include this. So now you see that all of them are same. That's precisely what happened here. So the point that I am trying to make is, you start with a relation and which is reflexive, symmetric, but not transitive. Then look at the underlying equivalence class. Now on this side you will add transitive pairs. Because of that, the relation is modified from a non-equivalence relation to an equivalence relation. On the similar line, one can also modify the equivalence classes by making use of properties like if A belongs to B, then B belongs to equivalence class of A. Then using the fact that it is an equivalence relation, you get to see that additionally these two elements have to come in. And that tells you that you look at any two equivalence classes, they are equivalent. And so in some sense, you can construct an equivalence relation from the given set of equivalence classes, or given a relation, equivalence relation, you can construct the set of equivalence classes. And they are, having one-to-one correspondence. You start with some set of equivalence classes that need not correspond to an equivalence relation. Then just like you add transitive pairs and convert a relation into an equivalence relation, same procedure can be adopted to convert set of some sets, need not be an equivalence classes, into set of equivalence classes. That's the message. It is a set of sets 1 3 2 1 3. Now you try adding something and it becomes 1 3 2 2 1 and 1 3. This is also a set of sets, but does this correspond to, this corresponds to a relation. The question is, does this correspond to an equivalence relation or not? And by observing properties and by making use of the properties such as symmetricity and transitivity, we get to add new elements. Thereby we take you to the set of equivalence classes. Most importantly, the properties that we observed just before, it is being respected in this case. So we saw that for this relation 1 1, 2 2, 3 3, the equivalence class of 1 was 1 and 2 was just 2 and 3 was just 3. For this one it is this and this. So in some sense, if you look at the set A equals 1 2 3, this equivalence class is trying to represent like this. This equivalence class is trying to represent the set like this. If you look at A cross A cross A is trying to represent 1 2 3. So it tells you something. So the set of equivalence classes and the underlying set has some nice interesting relation. What is that? We shall discover next.